My senior design project and the very last project I did at Georgia Tech was Inky, which was a neonatal incubator for a doctor in Ghana. He was absolutely amazing. And he mentioned that he needed incubators for his hospital. And he mentioned it to one of our senior advisors. Our advisor, Dr. Smith, created an entire project dedicated to trying to design a low-cost neonatal incubator for his hospital. And we signed up to do it, and we never looked back. This was what it looked like in the end, but it did not start off this pretty. Let's start Inky's story with my favorite part, which was, of course, the circuitry. The PCB was the hub for everything in the system. All the controls, the front panel, everything in the system talked to this circuit board. And one of our requirements was making sure that everything we were doing digitally in our microcontroller and the code that we wrote could be replicated in the analog design. If we ever lost power to the microcontroller or something happened, we were still able to do the heating function and the alarm with the analog circuitry. So we had our work cut out for us, and we had to have a way also to bring in power from the backup source if the hospital power went out. So it was a lot of work, but it was also a lot of fun. And it was the most realistic problem that I had to solve, I feel like, while being a student at Georgia Tech. So for us designing this circuit, every circuit starts as a drawing on a piece of paper and the thought of what functionality are we trying to get out of this circuit? What are we trying to do? And once we listed out all the functions that we needed and decided what we wanted to do and what parameters were guiding the design, we designed our circuits and decided what parts we needed, got parts ordered, found parts around the lab, and then we headed to the lab to see if our circuits actually worked individually. We didn't test them all together at first. We tested them individually to figure out if they were actually doing what we thought they were doing, the way that we designed them to work, and then later we put them all together. And this is a video I had of me describing our control circuit logic for the entire heating system. Look at
What's
me,
good, y'all?
so young,
it's
so
Ben
happy.
With Brianna here, and Brianna's gonna
So
take
excited.
it over and explain some control circuit logic for the heating system. Let's go.
So we have our temperature sensor hooked up to our oscilloscope and our reference voltage from our power supply. So if the reference voltage is higher than our temperature sensor, then we should get a low output. And if the reference voltage is lower than our temperature sensor, then we should get a high output. So that is what this circuit is testing. And so and so we have a high voltage as our reference, which is higher than our temperature sensor voltage, which is 200 millivolts, and we have a low output. And so when I make this lower than 200 millivolts, the output should go high.
And it does.
In which it does. And once we got each individual circuit working, we started to integrate and add it to the larger setup with other circuits just to kind of make sure slowly that everything worked by itself, and then we added it to the larger setup. We actually found a big piece of wood to set up our prototype circuitry on so we could move it easily around the lab and not have to take a bunch of little pieces with us everywhere we were going. So that turned out to be real clutch. So this video shows us running a heat test that I'll get into later, but the next step for the electronics team was to move our circuitry from the wood prototype and get an actual circuit board printed.